When a planet orbits around the sun, so here's a planet, and let's say here's the sun, and the planet is going around the sun, there is a potential energy that the planet has in terms of its distance from the sun, r. And the form of that potential is something like this. It's some constant a and b. These are constants. A and b are constants, positive constants. A over r squared minus b over r. So a and b are positive constants, and r is the distance from the planet to the sun, which is always going to be a positive number. Well, let's see if we can sketch this. What is this potential going to look like? Just a sketch. So let's see if we can plot u as a function of r, and we only have to worry about positive r's. R, the radius, the distance from the planet to the sun, is never negative. When r is small, then r squared is going to be even smaller than r, and 1 over that will be even bigger. So this term will dominate when r is small. So as r gets close to 0, the potential is going to look like a constant over r squared. And what does that do? That goes up to infinity. As r is big, r squared is going to be bigger than r, and so 1 over a bigger number is going to be smaller than 1 over a big number, or a big number and an even bigger number. So when r is large, it's going to be dominated by minus b over r. So it's going to be negative, and it's going to go like 1 over r. So it's going to look something like this. So it's negative and goes like negative 1 over r, or b over r. And then in between, well, these need to join up. So we'll just kind of join these up smoothly, come down, and then come up like that, something like that. Okay, so first, what we know about potential energies. Are we going to have a stable situation here, an unstable situation, a neutral equilibrium situation? Well, right here, if we are down here, what do we have? We have a minimum of the potential. So if the planet is at this radius, it's going to be, what, stable or unstable? Well, it looks like being inside a bowl, it's going to be stable. It's a stable type of orbit around the planet, around the sun, sorry. So what does this mean? It means that it's going to maintain a constant radius. Well, what would an orbit look like with a constant radius? It's going to look like a circle. So the planet orbits around the sun at a constant radius in a nice circular orbit. Well, what happens if the planet or whatever is moved away from that equilibrium? What's going to happen? Well, it's going to move back and forth. It's going to start to move back to equilibrium, but it'll have some energy, and then it'll get a little bit at a smaller radius, and then it'll go back and forth, like the object oscillating on the spring, back and forth. Might not be symmetric about this equilibrium point, but it's going to vary its radius, larger radii, smaller radii. Well, what kind of orbit does that look like? Well, that is an elliptical orbit, where at some points the object will be at a greater distance from the sun, and then it'll get in closer, and then, farther away, and it's going to be in an elliptical orbit rather than a circular orbit. All right, very, very interesting. What is this stable radii? What is this radius? Well, that's going to be where the force is equal to 0. In other words, where the potential is a minimum. So where is this a minimum? Well, let's differentiate and figure out where is that derivative equal to 0. So let's figure out what is du dr. Well, we've got a 1 over r squared term, in other words, an r to the minus 2. So differentiating that, we'll get a minus 2 times a over r minus 2 minus 1, which is r minus 3. So over r to the third. So minus 2a over r cubed. And then we'll have a minus and a b, and we've got r to the minus 1. To differentiate that, we bring down the factor of minus 1. That'll make that positive. And then we subtract another one, r to the minus 2, so b over r squared. There we go. So this is actually the negative of the force, right? So this will be minus F sub r. And we want to figure out where is this equal to 0? Where is the force 0? Where is that 0? Well, that will be where b over r squared is equal to 2a over r cubed, multiplied by r cubed, both sides. That will cancel this and give us a factor of r divided by b, and what do we have? R equals 2a over b. So whatever those constants are, 2a over b, that's going to be our equilibrium radius. That's where the planet will have a nice, stable, circular orbit. Okay, very, very good. What I'd like to do now is to go back to our definitions of potential energy and kinetic energy and see how these are related with the work to a concept of the total energy. We've talked about mechanical energy. Let's see if we can generalize that a little bit more. We have that the work done by our external force is the integral from 1 to 2 of F dot dr, and we've seen that that is from the work kinetic energy theorem, the change in the kinetic energy. And now with our new definition of potential energy, that is the negative of the change of the potential energy. Well, delta K is K final minus K initial, K2 minus K1. And this is the negative of delta U, which is the negative of U2 minus U1. In other words, the negative of that is U1 minus U2. Let's take U2 over on this side and K1 over on this side. What do we have? We have K2 and then plus U2 is equal to K1 plus U1. Here we have the sum of the kinetic plus the potential energy. This is what we call the mechanical energy. And this is the mechanical energy evaluated finally, and that's equal to the mechanical energy evaluated initially. So what is this telling us? ME for the mechanical energy, ME2 equals ME1. In other words, the value of the mechanical energy does not change. And we could choose our points, the initial and final points, any time we want. What this is telling us is that the mechanical energy is conserved. In other words, the value of the mechanical energy does not change during the motion. Even though there is some force acting on the object, the force that is actually doing the work, that is creating the potential energy. As the object moves, the sum of its kinetic and potential energy, what we call the mechanical energy, does not change. So the mechanical energy is conserved. This is a very, very interesting result. And we've seen this with the skier on the slope, that the kinetic plus the potential at the top was equal to the kinetic plus the potential at the bottom. Can we generalize this? What if there are other forces? Forces that are not conservative. If there are conservative forces, we could just add in another potential. We could have the kinetic plus the gravitational potential plus the spring potential plus whatever other conservative force potentials there are, and the total mechanical energy, which would be the sum of the kinetic and all of those potentials, would be conserved, so that the total mechanical finally is equal to the total mechanical initially. But what if there are non-conservative forces? What happens? How does that affect our result? Let's take a look at that. Even with non-conservative forces, we still know that the total work done acting on the object is going to be equal to the change in its kinetic energy. But now let's imagine that our total forces can be broken down into two parts. We have the conservative forces and then non-conservative forces. Non-conservative forces would be forces that do not conserve energy, so to speak. For example, well, let's just say that don't have a potential energy associated with them. For example, a pushing force, if you push on something, that would be a non-conservative force. A frictional force, that would be a non-conservative force. So whatever the total force is, let's imagine we can break it down into the two parts, the conservative forces and the non-conservative forces. The total work done is then going to be the integral from 1 to 2, from initial to final position, of the conservative forces and the work done by the non-conservative forces, or I should say the integral of the non-conservative forces. which will be the work done by the conservative forces, then plus the work done by the non-conservative forces. And that sum is still going to be equal to the change in the kinetic energy. But the work done by the conservative forces, remember we can write that as the negative change in the potential. So let's bring this over to the other side, and what do we have? We have the work done by the non-conservative forces will equal the change in the kinetic energy plus the change, plus the change in the potential energy, which is just the change in the mechanical energy. What we have is kind of a generalized work kinetic energy theorem. We might think of this as the work mechanical energy theorem, where in this case, rather than just having the kinetic energy on this side, we have the kinetic plus the potential energy on this side, the total of which is the mechanical energy. How do we change the mechanical energy of an object? By doing work on it with a non-conservative force. If there is no work done by the non-conservative forces, what do we have? We have zero change in the mechanical energy. We have the mechanical energy is conserved. It does not change its value. But when we have work done by a non-conservative force, we are going to change the mechanical energy. Let's take a look at an example of this. Let's say we've got a frictional force acting on an object. Let's see how that's going to affect our result, our mechanical energy.